Go back to the density matrix and Bloch sphere. So last time we already understand any density matrix can be represented by I plus A dot sigma divided by 2. And we know that last time I showed you that if A has the magnitude of 1, this density matrix corresponds to one pure state, right? So no problem. Any pure state, we know that is on the surface of the Bloch sphere. Right? So that this density matrix will correspond to a point on the surface of the Bloch sphere. Now, how do we understand a mixed state density matrix then? Now, first of all, of course, for example, I have alpha part of 1, beta part of alpha part of 0, beta part of 1, with alpha plus beta equal 1. Then its density matrix is alpha outer product of 0 plus beta outer product of 1, correct? And then we get this density matrix. I can express this into this form, A dot sigma. And how I express it, you just go through the math that I told you like in the assignment, you can find out them. Or it's very obvious, this is equal to I plus sigma z times alpha minus beta divided by 2. So what is the A here? The A here is, anyone know what is A in this case? For the Z. Can you give me the whole thing? 0, 0, and it's just only alpha minus 2, because in my notation here, I have the 2 outside, right? But again, because last time I have A and A dash issue, right? So that can be confusing, but from now on, I all call it A. This is the A vector. Make sense? So let's take a look. What is so special? Now, if I look at my Bloch sphere, right, and I say that in this particular case, you know what are the pure states. I have two pure states, 0 and 1. Now, for the 0, I know that it means it has plus 1 of the expectation value when it is projected to sigma z. It is plus 1. For 1, it has negative 1 of the value, right? But I only have alpha part of 0 and beta part of 1. So as a result, the FH value is going to be alpha minus beta, right? Plus 1 times alpha plus negative 1 times beta. And this turned out to the length of the A. Okay, so from here, I have a guess. I say that, well, if I have a density matrix, I express it as I plus A dot sigma. Then this corresponds to a mixed stage in which I have the two orthogonal states along this A. Along this A. This is A, right? The vertical direction is A. With which has the FH has the expectation value equals to the length of A. Okay? So the A represents the mixed stage with expectation value along A vector. Okay? And the expectation value has or is the length of A. So, is this okay? So let me see. How do I actually need to say something? Right? Maybe I can add a few more sentences from in the next page. So I will say so. Right? From the previous slide. So A, the magnitude of A, right, is the mixed state. No, actually, I need to copy my original sentence. Represent the mixed state with expectation value along a vector. Or maybe it's the mixed state, it's the expectation value of the mixed state. So basically, I don't know if I'm clear about this, right? But let me show another more complicated example. Then maybe it will be clear. Let's consider a general state. Rho equals to I plus A dot sigma. This is the general state, right? So I want to see what is the expectation value of rho along A dot sigma. Right? Basically, I have a matrix which is I have a operator A dot sigma due to the external magnetic field, which is A dot sigma. You get this because the magnetic field is along the A direction. What is the expectation value of rho on this? This is given, right? So how do you find it? Do you remember how to find the expectation value if I given a density matrix? Trace of rho times the operator, correct? That's how we do it, right?
That's by the definition of the
inner product. Yes, the inner product. Yeah, but that is what we proved earlier also, not just from inner product. Yeah. We proved that it turned out to be the inner product. So what is this? How do you operate it? Well, this is I plus A dot sigma divided by 2, the whole thing times A dot sigma, right? So I can do a distribution law. This is equal to trace of A dot sigma divided by 2 plus A dot sigma times A dot sigma. So we need to be careful about this when we do this multiplication. A dot sigma is vector dot vector, but it becomes a matrix. So this is matrix times matrix. This equals to the trace of A dot sigma divided by 2 plus the trace of A dot sigma times A dot sigma. What is the value of the first term? Do you remember the property of the Pauli matrix? They are traceless, right? So you just expand them. They should give you sigma, right? Give you 0, right? Because A dot sigma is just equal to AX times sigma x plus AY times sigma y plus AZ times sigma z. You take the trace, they are all 0. Okay? Then how about the second term? Second term, we need to expand them a little bit, right? If you go through all the, I'm going to take these 2 out. If you go through all the math, this is just AX sigma x times, let me do it, AX sigma x plus AY sigma Y plus AZ sigma Z, the whole thing square, right? Because this is A dot sigma is AX sigma X, AY sigma Y, AZ sigma Z, then the whole thing square, right? And then you will do all the combination of the terms. But you know that there are only two types of combination. Either you have sigma I square or sigma ij, sigma I times sigma j. Correct? Either sigma x, sigma y, or sigma x, sigma y, sigma x, sigma z. But from the trace perspective, do you still remember? The trace of sigma I squared equals to what? I think it is 2. No, yeah, it is 2, because sigma I squared equal to what? Identity, right? So this is 2. And what is the trace of this guy? If they are not the same?
0.
Yeah, it's delta ij, 2 delta ij, right? So this is 0, right? Just remember this. Trace of sigma I, sigma j equals to 2 delta ij. Yeah, so here, from here, I only have a few terms left. Those are the terms that has sigma x squared plus sigma y squared plus sigma z squared, right? So this is just equals to ax squared plus, ax squared sigma x squared plus ay squared sigma y squared plus ac squared sigma z squared. Right? And then we say that trace are equal to 2, right? So this is just equal to the trace. I mean, we take the trace, so we don't need the trace anymore. We take the trace inside. So this is just equals to ax squared plus ay squared plus az squared. I think I did something wrong. Okay, I did not completely correct. This is equal to a squared. First, does this make sense? Right? Because you just expand it, right? You will see that you either get sigma x squared, give you trace of 2. So this 2 got cancelled, or 0. So all this 0, ignore it. And those who give you 2 must have ax squared, ay squared, az squared, right? And you add them together, it is the length square of A. So indeed, the expectation value along this axis, right, it does give you the expectation, but this is not exactly correct. I forgot to write one thing. Actually, what I'm care about is not along A dot Z. I want to normalize it. I care about along the unit vector here. So I want to divide it. I will need to divide n, which is the unit vector, which is A divided by A magnitude. So this is a normalized unit vector. Your A can be smaller than 1. But what I'm care about, the operator we should use is not A dot sigma Z. It should be the n dot sigma Z, the normalized version, times sigma Z. So I missed this one. And because of this, I need to add back what I missed. So here I need to divide by the A, right? So from here on, I will divide it by the A magnitude. Sorry for this. Divided by the A magnitude, divided by the A magnitude. And here I still have A magnitude. So here divided by the A magnitude. So this becomes just the magnitude of A, right? So here I just take a square root. Why come I don't have enough space? So what did I do? First of all, I just go through the math. These are just purely math. I say that the expectation value of this density matrix, or of this mixed state, along A dot sigma normalized along that direction, when the operator is along that direction, is just equals to the length of A. Okay? So for every density matrix, we always can decompose it into A dot sigma. Yeah, we always can do that. But then this A will represent a particular direction. So in this direction is the average value or the expectation value due to this A dot sigma will be equal to the length of A. Now, but you have many different mixed states that can give you the same density matrix. Right? Density matrix is not unique. Let me show you, I'm not going to show this one. Before that, I have.
Could you explain that last step at the very end again?
Which step?
The bottom left written red.
Bottom left here?
Yeah.
Yeah.
So that it goes to just A square anyway.
Because when you do this square, right, you have x plus y plus c, right? You do the square, you get sigma x square, sigma x sigma y, sigma x sigma c, sigma y square, sigma y sigma x, right? All these combination. And then for the one that is the same, when you apply the trace, it becomes 2. But for those that are different, it becomes 0. So because there I have 9 terms, right? So I only have 3 terms left.
Right, no, I get that. I mean, just the last one where you go from that trace.
And then when you apply trace to sigma x squared, you get 2. You apply the trace to sigma y squared, you get 2. So these 2 cancel with this 2. Okay. So you only have ax squared plus ay squared plus ac squared, which is the magnitude square, right? And then I divide it by the a magnitude. That's why it becomes the square root. So that's why I have.
I forgot the trace.
The trace what? Yes, distribute due to its addition, right? So you can distribute it. Yeah.
Question.
Yeah.
So the definition of A in the pure state case, is it the same as in this slide, the next step? So we started with the pure state, right? When you were doing the derivation, and then we came to the mixed state, and then maybe 2 examples of mixed state. So in all these derivations and scenarios, the definition of A vector is the same?
But the A is going to be 1. The length is going to be 1. Pure state and mixed states are the same. We follow the same formalism. Okay? But for pure states, it's kind of like you, for pure state, it just corresponds to 1 vector on the sphere. But for mixed states, it can be any ensemble, give you the same density matrix. But one of them are very special. The one that is special is the one that has an orthogonal state along A. I'm going to explain that. Let's take a look. I know this is messy. I think this is what I want to show. Let's look at, again, the summary of between the, I try my best to explain. It's difficult. I hope you just ask me, you have questions. The relationship between the mixed state density matrix and the Bloch sphere. Definitely, density matrix, we cannot plot on Bloch sphere, right? Because Bloch sphere represents the state. So you can only put the real pure state. Every density matrix can have different ensembles. For example, 50% 0 plus 50% this combination. I have 2 pure states, but both 50%. We already done that. You go through the math. You will find that we did not do that for the red one. This one, they just trust me, has the same density state as this matrix, as this ensemble. 85.36% of this pure state and 14.65% of this pure state. You just go home and try. They both have the same density matrix. equals to 0.75, 0.25, 0.25, 0.25. Do you agree with this? You can have different ensembles, but you have the same density matrix. Or you feel this is strange. Yeah, you can do that. You can have the same density matrix. Right? That's what we said before. However, one of the group is very special, which is the red here. It has a mixed state, very simple mixed state, only 2 of them. You can have 1 trillion of pure state and form the mixed state, right, as I said earlier. But they give you the same density matrix. But one group is very special. For this density matrix, it is the one that has the mixed states only 2 and orthogonal to each other. Go to do a math. You find these 2 are orthogonal to each other. Just do an inner product. And you see that already. This number equal to this, and this is negative. You just do a squared, just do the dot product, you find that is 0. Okay? So in any density matrix, and then in any density matrix, we are able to express in this way, right? So basically, on the Bloch sphere, right, I have Y, I have Z. For that particular density matrix, you can always see a A. In this case, is actually in this direction. This is A. It turned out to be 45 degrees in this case. If I call this V1, this V2, this is V1, and this is V2. So for any density matrix, you will have an A for sure, right? You can always factorize to this, we proved to you already. And this density matrix can be composed by 2 orthogonal states here, 2 pure states. They are orthogonal to each other. They give you the same density matrix. And what is the expectation value of this? First, the A represents the direction of these red states on the Bloch sphere. Yeah.
I'm confused by the word orthogonal here. Typically, orthogonal, I always understood something that's 90 degrees.
Very good. Why I call this orthogonal? Because I'm talking about the qubit state. How do you define the qubit state being orthogonal? How do you define 2 vectors are orthogonal? How do you do that?
Well, you take the dot product.
You take the dot product. You just take the dot product of these 2, you will find it is 0. But then you say, this is not orthogonal in 3D space. It doesn't matter. Remember, what is the 3D space? That is not the real state of your qubit. You just map it to the Bloch sphere. 0 is not pointing up. 1 is not pointing down. Remember? We just embed it to the real 3D space. And that's why I keep saying, do not think that 0 and 1 are not orthogonal. Do not say 0 plus 1 equals to nothing. Because we just embed in the 3D space. When you say these 2 are not perpendicular to each other, you're thinking about the 3D space. But what we're talking about is the qubit state. So in the Bloch sphere, if you are in opposite poles, then they are orthogonal in their qubit space. Just, yeah.
So it says A represents the direction of red state on the block. Earlier I thought A represented magnetic field.
Oh, no, the 2 represent 2. So it represents one thing is that it is the direction of these 2 orthogonal states. So in order to get this density matrix, you can have different type of ensemble of mixed states. And one of them is along A, okay, that will give you this density matrix also, which is this red state. Okay? We have not done any measurement. We just say that the 2 states along this A will give you the right density matrix also. It can be have,
I guess we just don't get it.
No, we don't have to go to magnetic field yet. I will talk about that. But this one, is it okay? I just additional. It has not. There's no contradiction to the magnetic field I said. By the way.
So the magnetic field is always moving in a direction.
Well, where the state is has nothing to do with where we put the magnetic field. Right? I'm talking about a mixture, an ensemble of mixed states. It doesn't matter. It even doesn't matter if I apply the magnetic field. Let's say there's no magnetic field. And I'm saying that you can have different ensemble that give you the same density matrix. One of them is along this A direction, and they are orthogonal to each other. For example, this one, the purple one, they are not orthogonal to each other, and they are not along this A direction, but they give you the same density matrix. And one of them is very special, is this rest state. And they are the result, the rest state is the result of the diagonalizing the matrix. Or we just say that they are the eigenvector of the density matrix. Of the density matrix. It turned out to be the eigenvector of the density matrix. Yeah.
So, okay, is it fair to say that, let's say, I point the magnetic fields in sort of an arbitrary direction.
No, nothing with magnetic field yet. Let's don't go to magnetic field. Finish this first. Do you agree with this? I'm just saying that there are many ensemble can give you the same density matrix. And one of the ensemble is very special. They are along the A direction of the Bloch sphere with only two states and orthogonal to each other. That is the only message I'm telling you here.
But then the application here would be...
No, don't think about application. Is this clear first? Is it completely clear? That is very important. Yeah.
If there is the same density matrix, like V1 and V2, where will that line be pointed on this Bloch sphere?
Well, suppose there is another what?
We have different equations, like
Ensemble.
Yeah.
There can be many different types of ensemble, and not just two pure state. You can 1 trillion pure state. Yeah.
Yeah. If there is
Yeah. Another one. Yes.
the same density,
Yes.
then where will that V3?
No V3. V1 is about this one. V2 is this one. Inside the same ensemble. If you add another ensemble, then it is not belong to this ensemble already. Okay, yeah, it can be any point on the Bloch sphere, right? Including this one and this one at some place on the Bloch sphere. But only one of the combination only have two states, and both of them are along A, and they are orthogonal to each other. And that is the eigenvector of this density matrix. Yeah.
I'm sorry, when you said A is a list of 3 numbers.
Yes.
Or you can think of it as one vector.
A vector,
three
yeah.
states. How does that relate to 2 different vectors in the state space?
No. A, sorry, then maybe this one confused you. I'm just saying that this direction is A. That's all I'm trying to say.
Okay.
So you have a vector A, then you have this side and the other side, right? Then you have 2 possible vector that you cut on the Bloch sphere. Yeah, good point.
So,
Yeah,
so is that why you have, I was trying to understand B and Y. Why do you think B and
C and,
Y? So when you draw...
well, because it happened that this one is along C and Y, on the C and Y plane. You just go back to try the theta and phi. So it happened to be that, yeah. Okay, just an example, numerical example. Yeah.
Is it true that then for it? No, never mind. Already answered them.
Okay, so this is the message I want to say, right? And then we go back to this confusing thing, right? I know it's very confusing. Maybe I should change the way I teach, or maybe I don't understand it well. Now, if you have a magnetic field apply along this A direction, the operator is A dot sigma, and the expectation value is going to be the length of A. It happened to be the length of A. Because now if you just look at this simple example, one is pointing in positive direction, another is pointing in the negative direction of A. Then of course the expectation value is the length of A because, I prove it, not of course, we prove it here, right? So I know this is very confusing. It confused me a lot also, right? So I still cannot explain you. But I just want you to step back. At least you have this idea. A density matrix can be corresponding to the pure states. Then, of course, it must be a point on the Bloch sphere because it's a pure state, right? So this density matrix corresponding to the point on the Bloch sphere. Done. A mixed state is a mixed state density matrix corresponds to many different ensemble of mixed states. Right? You can have many different dots on the Bloch sphere, but they have different percentage. There's no good way to represent this one in the Bloch sphere. But turn out that one of the combination is the 2 points along the Bloch sphere in the A direction. This one gives you the same density matrix. And the expectation value is just the length of the A. For other points that are not that special, like the purple case, or 1 trillion pure state case, you plug in, you still get exactly the same expectation value. Okay, by math, we proved that already, right? Because they have the same density matrix, then of course they have the same as expectation value. Right? So this is just an idea, right?
So,
Right? I still have a, yeah.
in the case, the purple case, okay.
Yeah, purple case, it represents two states that are not orthogonal, has nothing to do with this A, although you decompose to have A, right? But their expectation value along this is still A. Turn out to be that.
So if we can figure out the decomposition of our density matrix, we can quickly pull out what the eigenvectors are, right? Because it's just going to be the 2 points, like what the two pure states are, because they're just going to be the two, points on the Bloch sphere that intersect with A.
That cut the Bloch sphere. Yes, yeah, you can say so, yeah. Mathematically might not give you too much convenience because you can just diagonalize the row. But it's just the understanding. Because that confused me before, this might not be an orthodox way of teaching this, but I want to share with you my understanding.
So they're unique, right? There's only one set.
Yeah, except for the face. Yeah, they are unique.
It's the same. You're just putting it in phases, but
You can say that it's just like you put it in the z basis, and this corresponds to 0 and 1. So just like this very simple and special case we did at the beginning, but now it's along A. Yeah. So actually, this line I did this was intended to do some more math for this stuff, but I don't think we will have time or necessary to go through this math. It's not necessary really. I would just say see previous stage. So previous slide. So you need to listen to the video if you forgot what we discussed, right? So let's move on. So we are done with density matrix, right?